Look at your arm right now. Whatever color it is, that color is the end result of a 100,000-year experiment your ancestors didn't sign up for. Every human who ever lived, going back far enough, had dark skin. Every single one. So how did we end up with the entire spectrum we have today, from deep brown to pale pink? The short answer is sunlight did it. The long answer involves vitamin D, folate, at least one extinct human species, and a piece of skeleton found in a cave in England that broke everyone's assumptions. Let's get into it. Start about 2 million years ago, in East Africa. This is where our genus, Homo, first shows up, and the environment is brutal sunlight. Near the equator, UV radiation is intense. All year round, no breaks. And early humans at this point had probably just lost most of their body hair. That's a problem, because bare skin under that kind of sun is a target for skin damage. So evolution did something logical. It cranked up melanin production. Melanin is the pigment that makes skin darker, and it works like natural sunscreen. It absorbs and scatters UV radiation before it can damage the deeper layers of skin. Dark skin, in equatorial Africa, wasn't a cosmetic feature. It was survival gear. Here's the specific danger it was solving. UV radiation breaks down folate, which is a B vitamin your body needs for cell division and, critically, for healthy fetal development. Anthropologist Nina Jablonski has done a lot of the key research here, and her argument is pretty simple. If folate gets wrecked by too much sun, you get birth defects and lower fertility. That's a massive evolutionary pressure. So populations near the equator that had darker skin, and therefore better folate protection, had a real reproductive advantage. Over hundreds of thousands of years, that adds up to an entire population being dark-skinned. So if dark skin is the winning strategy, why isn't everyone still dark-skinned? Here's where it gets interesting. Around 70,000 years ago, give or take, groups of humans started migrating out of Africa. Think about what that actually means for your skin. You're used to intense, direct, year-round sun. Now you're heading into Central Asia, into Europe, into places where sunlight is weaker, especially in winter, and the sky is gray half the year. And that creates a completely different problem. Remember, melanin blocks UV radiation. That's great when there's too much sun, but your skin also needs a certain amount of UV exposure to make vitamin D. Sunlight hits your skin, and a compound there converts into vitamin D, which your body needs for calcium absorption and bone health. Too little vitamin D, especially over generations, means weak bones, rickets in children, and again, lower reproductive success. So now you've got the opposite pressure. In low sunlight regions, dark skin starts working against you. It blocks too much of the UV you actually need. This is what researchers call the vitamin D hypothesis, and it's basically the flip side of Jablonski's folate argument. Same mechanism, opposite direction. Populations in these northern regions that happen to carry genetic mutations for lighter skin could make more vitamin D with less sunlight. That was suddenly the advantage. So lighter skins spread, generation by generation, not because anyone chose it, but because it worked better where they'd ended up living. Now, here's a twist that surprises most people. You'd assume skin got lighter gradually and steadily as humans moved north, like a dial slowly turning down. That's not what happened. In 2018, researchers studying ancient DNA from a roughly 10,000-year-old skeleton found in Cheddar Gorge in England, nicknamed Cheddar Man, discovered something that broke the standard assumption. His DNA suggested dark skin in Britain 10,000 years ago. Combined with blue eyes, geneticists, including Johan Diekman and paleoanthropologist Chris Stringer, working with the Natural History Museum in London, helped confirm this analysis. It meant that light skin didn't spread through Europe as fast as everyone had assumed. People had been living in cold, low-sun environments for tens of thousands of years while still being dark-skinned. So, what actually sped things up? This is the part that's hard for modern people to picture, because we assume evolution is one smooth process. It isn't. Diet changed everything. Here's the second major shift. Once agriculture spread across Europe, roughly 7,000 to 8,000 years ago, human diets changed dramatically. Hunter-gatherers were eating fish, organ meat, and animal fat, all naturally rich in vitamin D. You get your vitamin D from food, you don't need as much from sunlight, and dark skin can hang around longer without a cost. But farming populations shifted heavily toward grain-based diets. Wheat and barley don't contain meaningful vitamin D. So suddenly, sunlight became the main source again, in a place that barely gets any. That's when the real pressure for lighter skin kicked in hard. Geneticist Sarah Tishkoff's research on pigmentation genes across African and global populations shows just how many separate mutations were involved in this, genes like SLC2-4A5 being one of the biggest single contributors to lighter skin in European populations, and it appears to have spread relatively recently, within roughly the last 8,000 years. Think about that timeline for a second. Humans left Africa around 70,000 years ago, but some of the strongest genetic signatures for light skin only became common in the last 8,000. That's not a slow fade. That's diet forcing a much faster shift, later than you'd expect. And there's one more twist to add here. Modern humans in Europe and Asia also picked up pigmentation-related genes through interbreeding with Neanderthals and Denisovans, other human species, who had already been living in low-sun environments for a very long time and had already adapted. So some of what we think of as European or Asian traits weren't invented fresh. They were borrowed from cousins who'd already solved the problem. So by this point, you've got a picture that's way messier than dark skin near the equator, light skin far away. It's closer to a patchwork, shaped by migration timing, local diet, and even genetic mixing with other human species. Now, compare that to today. We live in a world where a lot of us barely go outside. You commute in a car, work under fluorescent lights, and maybe get direct sun for 20 minutes on a walk to lunch. And it's created an odd modern irony. A huge number of people worldwide, including plenty with lighter skin evolved for exactly this kind of climate, are now vitamin D deficient anyway, not because of skin tone, but because they're barely getting sunlight at all. The evolutionary solution outpaced the modern lifestyle that eventually made it almost irrelevant. Meanwhile, people head to tanning beds or spend money on vacations specifically to darken skin their ancestors spent thousands of years evolving to lighten. And people with naturally dark skin, especially those who've moved to low sunlight countries, face a real, modern version of that original vitamin D problem, just now solved with a supplement bottle instead of a genetic mutation. So here's the actual answer. All the way through, ancient humans didn't lose dark skin because dark skin was a problem. They lost it because their environment changed, sunlight dropped, diets shifted, and the same trait that once saved them started costing them something else. Skin color was never really about identity. It was about vitamin D, folate, and whatever your local sky happened to be doing. And that's the part that's almost funny, if you think about it long enough. The one trait humans have used for centuries, to sort each other into categories, build hierarchies, and decide who belongs where, is really just a sunlight receipt, a record of where your ancestors happened to end up standing.